All right. So in this example, we have a Boeing 747. It starts its takeoff run at time t equals to zero. Uh, we are given the information about the normal forces exerted on its tires at A and B, right, where the contact points are with the ground, point A and point B. We are told that at point A we have the force applied to the body at which is 175 kilonewton, and at B the force is 2800 kilonewton. Now, assuming that the forces are constant, which is a pretty big assumption, and pretty major assumption, I would say, these forces are constant, and if we can neglect all the forces other than thrust T, which is applied to the whole structure because of the uh, engines of the plane, right? So it's pushing the plane forward. If that's the only horizontal force applied to this body, to the airplane's body, we want to find out how fast is the airplane moving after 4 seconds. So let's see how do we deal with this. Well, as always, when we are dealing with a problem in dynamics, right, when it comes to kinetics, we start with free body diagram. That's always a must. That is a must, and you always have to do it. Otherwise, things can go wrong. So I'm going to try to draw the rigid body. Well, I can't really draw a plane, so let me see what I can do. I'll do my best. Oops, not the color I want it. All right, so let's assume that this is my plane. It looks like a fish. I'm gonna save it by adding this there. So we are going to have one tire here, and let's see another one there. So looking at the forces, I have one normal force here at A, called NA. I have another normal force there at B, NB. Center of gravity is given, it's there, so I'm going to put it approximately around the same place here. That would be, let's say, this one. So apply the mass at the center of gravity, mg. As I said, we're looking at this like we were looking at a particle. Right? But this time the particle is the center of gravity. And from there, this is the equivalent is equal to I'm going to look at the kinetics, right? The kinetic diagram. So this is free body diagram, and then God help me, I have to draw the plane again. Let's see how similar would it be to the first one. Okay, so same fish, put it there, and then the plane's wing. Well, close enough. Okay. On this one, the only let me fix this part. The only force, or the only I would say the component we have on a kinetic diagram would be, since it's a translational motion, well, it's moving to the left because the thrust force is toward left, so I'll just put it right there, and this would be MA. MA, going to left, towards left, and this is kinetic diagram. Kinetic diagram. Okay, so let's start with summation of forces equal to ma. Right? We have x and y. Let's take this. Let's just put it here. This is x, and this is y. So summation of forces in x is equal to ma in x direction, and I always take the direction of the motion as positive. Nothing happens if you don't do it, but in the future, probably next future courses, you will see that that is a very good practice to always take the direction of the motion as positive. So this is positive, which means, well, the only thing I have, oh, apparently I forgot the main thing I had there, and that's the thrust force. Right? It's applied somewhere here. There you go. That was missing from my free body diagram. This is the center of gravity. Let's see if I can put it there. This is center of gravity, CG. It's represented by this circle on our structure. Now, okay, so only components we have in x direction are t and m, so this pretty much means t is equal to ma. Right, that would be my first equation. Now, summation of forces in y direction is equal to m-a-y. Right? The airplane is not moving, so doesn't matter which direction I take as positive. The airplane is not moving. Well, there is no component on kinetic diagram in the y direction, so this is 0. Right? That would be 0. And what I get there is NA. Only thing I have is the components from free body diagram. So NA plus NB would be equal to mg. This is going to be my second equation. Now, on these equations, I know what NA is, I know what NB is. I don't know T, I don't know M, and I also don't know what A is. So I have 3 unknowns. Right? These are 2 equations and I have 3 unknowns, which means that I need another equation. As I said before, since it's a rigid body, we care about the geometry and where the forces are applied. Right? It's not just a particle anymore. So forces can be applied on different places on a rigid body. And I'm going to use the third equation, which basically tells us the moment or the summation of all the moments about any point about on the body should be 0 since it's not rotating. So let me see if I can put it as a comment here. Airplane isn't rotating, so sum of the moments let's take them about the center of mass. Since I have all the dimensions that I need, I know that the distance between all these forces and the center of gravity. So the best possible point I can go with is the center of gravity, center of mass of the moments. Let's say about its center of mass. Oops. Use center of mass and center of gravity interchangeably. So sometimes they say center of mass, sometimes they say center of gravity, but they're pretty much the same. Is 0. Right, center of mass is 0, which means I can write summation of the moments about center of gravity is equal to 0. I'm going to take counterclockwise. Direction is positive. Since it's 0, it doesn't matter which direction you take as positive. There is no motion. There is no rotational motion. So I'll take counterclockwise as a positive direction, which means I will get NA times the distance it has. Let me see where we are. Okay. So NA is there. And then I have to find the distance it has from the center of gravity, which is 26 minus 2, so that would be 24. And the direction is in this direction, right? NA times the distance, and the direction, the moment it creates about center of gravity is counterclockwise, so that would be negative. So this gives me minus 24 NA. Right? NB, well, the distance between NB and center of gravity is 2, so NB times the distance, and the moment it creates is counterclockwise, so it's positive. So plus 2NB. And the last thing I have, well, the mass is passing through the center of gravity, so I can get there is no moment created by that force applied to a structure about center of gravity, so I can discard that. I don't need to be worried about that. And then I have thrust. Thrust, based on the dimensions we see here, well, this is 3 meters, this is 5 meters, 5 minus 3 is 2 meters. So thrust is 2 meters below the center of gravity. So T times 2, and it's creating a moment in clockwise direction, so that would be negative. So this becomes minus 2T is equal to 0. That would be the third equation. Now I have 3 equations and 3 unknowns. My unknowns, what are they? They are T, the thrust force that I don't know, the acceleration that I don't know, and the mass of the structure. So if I write it this way, give me 1, 2, you can solve these equations. You can find one value from here. Let's say you can find T from this equation, put it in this one, the third one, then second and third equations are going to be 2 equations and 2 unknowns. You know the values of NA and NB. NA is 175 kilonewton, NB is 2800 kilonewton, and you can just solve this these values. You can solve for these unknowns, T, A, and M. I'll just give you 2 values that we care. T is 700 kilonewton, and acceleration turns out to be 2.31 meter per second squared. You can also find the value of mass. I didn't do it, but you will get that value too. Once you know the acceleration, so the problem is asking for how fast is the airplane moving at t equals to 4 seconds. Once you know the acceleration, well, this is a constant value, which means the whole motion is motion with a constant acceleration. Remember from kinematics, when we're dealing with a particle, we can easily find the velocity after some given time. Then v would be at. Right? For a motion with a constant acceleration, we saw that this is this holds. This is the correct equation. Right? It's 2.31, and then time is given 4 seconds. That will give you 9.23 meter per second for the velocity of this airplane after 4 seconds, assuming that we can ignore all the forces except the thrust T that is applied to this structure.